All right, welcome back. In our last explainer on paper 38, we absolutely nailed down a huge result, the twisted bird map mixes. We even got a decay constant. But, getting an answer like that just leads to the next big question, and that's exactly what paper 39 is here to answer. So we know it mixes, but how fast?
So paper 38 handed us this decay constant, theta, and proved it was strictly less than 1. That's the mathematical proof of mixing. But a constant is just, well, a number. What we're really after is the rate of that mixing. How do we quantify that speed? That's the core mission of paper 39.
So here's our game plan. First, we're going to translate that decay constant into an actual rate. Then, we'll get into the formal definition of the mixing rate exponent itself, right before we unveil the paper's big, unconditional result. After that, we'll explore a couple of potential pathways to make that result even better. And we'll wrap up by framing the key open questions as conjectures about how the system behaves at the edge.
Okay, let's dive into that first step. We're taking the abstract decay constant from paper 38 and turning it into something we can actually work with, a concrete measure of mixing speed. The paper's solution is to introduce this new quantity, the mixing rate exponent, sigma. The definition is beautifully simple. It's just the negative logarithm of that decay constant, theta. And since we know theta is always less than 1, its log is always negative, which means sigma is always positive. This gives us a really direct positive measure of how fast things are mixing.
And here's the key thing to remember. The relationship is straightforward. A larger sigma means faster mixing. A sigma that's getting closer and closer to 0 means the system is really slowing down, almost grinding to a halt. So that worst-case theta we found in paper 38, well, that's going to give us our minimum speed, our baseline value for sigma.
All right, let's get a bit more formal with the definitions now. The paper actually gives us two different, but equivalent ways to formulate this mixing rate exponent. Each connects to a different aspect of the underlying operator theory.
So definition 1 is the one we've just been talking about, straight from the L1 decay constant. Easy enough. But definition 2, this one's a little deeper in the operator theory. It defines sigma using the spectral radius of the remainder operator r. You can think of this as isolating the part of the system that's responsible for the decay, completely separate from the stable long-term behavior. It's a powerful way to look at it.
Now, here's the crucial point. Even though these two definitions come at the problem from different angles, they totally agree where it counts. Proposition 2.3 confirms that for all 27 of our certified parameter cells, these two definitions give the same numbers. And, most importantly, they both point to the exact same worst-case value for sigma.
And that brings us to the headline result of paper 39. This is the paper's core contribution, and it's an unconditional one, a hard, explicit, lower bound on the mixing rate.
And the number is approximately 0.1370. Where does that come from? It comes directly from taking the negative log of that worst-case theta from paper 38, which was 0.8720. Theorem 3.1 is what cements this as our explicit and unconditional floor for the mixing rate exponent. If you look at this table, you can see exactly where that number comes from. Across all 27 of our certified parameter cells, the absolute slowest mixing happens right here, with the alien kernel at an epsilon of 0.80. That's what gives us our lower bound. And just for a little context, look at some of the other parameters. The Lorentzian kernel, for example, mixes way, way faster, with a sigma that's more than 15 times larger.
So Theorem 3.1 makes it all official. It establishes for all parameters that sigma is guaranteed to be at least 0.1370. But here's the really crucial part. Remember that Keller-Liverani persistence argument from paper 37? The one that ensures the spectral gap is robust? Well, because of that, this bound isn't just valid at those 27 specific points we tested. No, it holds across the entire continuous parameter space. That's what makes this a truly powerful, uniform, and unconditional result.
So, we have a bound. Great. But is it the best bound? The paper then shifts gears and lays out two completely different analytical strategies that could, potentially, lead to an even sharper lower bound for sigma.
They're called, simply enough, Route 1 and Route 2. Route 1 is considered a pretty low-risk approach that's based on a direct analysis of the remainder spectrum. Route 2 is a bit more ambitious, a medium-risk strategy that uses something called projective metrics on a cone of positive functions.
So let's look at Route 1. The idea here is to use the Lasota-Yorkin inequality from way back in paper 34 to directly constrain the spectrum. The problem? Well,
It works, but it's just not strong enough. The inequality itself isn't tight enough to give us a better bound than what we already have. So without some fundamentally new geometric insight to improve that constant, this route is basically a dead end for now.
Route 2 is definitely more ambitious, but it's also a lot more promising. The idea is to use this really elegant geometric tool, a Hilbert projective metric, to prove that our operator is a contraction. If we can show that, it would directly give us a better bound. But, and this is a big but, it's all conditional. It depends entirely on verifying three critical hypotheses. First, that the operator keeps functions inside a specific cone of positive functions. Second, that the geometric distortion from the operator is bounded. And third, that this all leads to a contraction factor that's genuinely better than our current bound.
And this leads us to the first major open question for Route 2. Does the operator actually preserve this cone of positive functions? We can't just assume it does. It's a real question, especially when our parameter epsilon gets close to the boundaries of our interval, near 0.70 and 1.10.
The second question follows right from that. Let's say the cone is preserved. What about the distortion? It's totally possible that as epsilon approaches the boundary, that cone gets stretched so much that the distortion just blows up. And if that happens, our contraction factor would approach 1, and the whole method would fail to give us any uniform improvement.
These big open questions about Route 2 bring us to the paper's final section. This is where these challenges get formalized into a set of concrete conjectures about the system's behavior right at the edge of its parameter space.
Okay, so there are three main conjectures here. Conjecture 6.1 is basically the optimistic goal of Route 2, that a real, strict improvement to the bound actually exists. Conjecture 6.2 is that there's a uniform gap keeping sigma away from 0. Now, technically, Theorem 3.1 already proved this, but it's stated here just for logical completeness. And finally, conjecture 6.4 suggests that the boundary where mixing stops, where sigma equals 0, is something we can actually reach within the parameter space we're studying.
So, to wrap up what paper 39 has accomplished, it really comes down to four things. It formally defines the mixing rate exponent sigma. It establishes a hard, unconditional lower bound on that rate. It frames a really clear, conditional theorem for how we might improve that bound, and it articulates the remaining questions as three concrete conjectures, which basically sets a roadmap for future work.
Now, it's also really important to be clear about what this paper does not do. It relies completely on the theoretical and numerical work of the previous papers. There are no new computer runs, no new kernels being tested, and absolutely no claims that this 0.1370 bound is the best possible one. The analysis is strictly confined to the existing framework.
And that sets the stage perfectly for paper 40. The path forward couldn't be clearer. We have to go back and directly confront those hypotheses from Route 2. Can we rigorously prove, or maybe disprove, the cone preservation and uniform distortion conditions? The answer to that question will tell us whether a fundamentally better understanding of the system's mixing rate is actually within our reach.